Hello, I'm Shashwat Khandelwal and I will be presenting our work, a lightweight multi-attack CAN intrusion detection system on hybrid FPGAs. This work was done by me and Dr. Srijit Shankar in the Reconfigurable Computing Systems Lab at Trinity College, Dublin. We first look at the overview of our presentation. We will first talk about automotive networks, then what is controller area network, its security threats and vulnerabilities, the existing solutions as intrusion detection systems for those vulnerabilities, then the gaps in those existing solutions, followed by our proposed intrusion detection system architecture with results and conclusion. Vehicles today contain more than 50 electronic control units in vehicles to enable safety and comfort services to passengers and vehicles. For these ECUs to communicate, there are a variety of communication networks that are present in the vehicle, ranging from local internet network for low-cost applications with speeds of 10 kbps to emerging automotive Ethernets, which have speeds up to 10 Gbps for diagnostic purposes. Controller area network, with its high speed, low cost, high robustness and flexibility, has become a de facto industry standard for such communications. It serves critical and non-critical functions in vehicles with a range of properties including broadcast-based mechanism sending for messages and with speeds up to 125 kbps to 1 mbps. CAN, though, has some vulnerabilities. It was designed in the 1990s for closed networks where vehicle could only be accessed physically and it was hence considered secure. Access to the outside world with systems like advanced driving assistance systems have exposed vulnerabilities in CAN. Lack of encryption and authentication techniques make CAN networks inherently insecure to sniffing and message injection attacks. Examples attacks involve, due to the broadcast nature of controller area network, a compromised ECU can carry out passive eavesdropping or sniffing attacks, which can be enabled through malicious code or aftermarket extensions. This leads to a complete loss of user privacy and critical network information. Due to the lack of sender authentication, the compromised ECU can also carry out DOS and denial of service and fuzzing attacks, which directly compromises the safety of passengers and can fully disrupt normal vehicle functioning. There are some existing solutions that were proposed to mitigate these issues that relate to the controller area network. Early rule-based intrusion detection systems correlated previously known attack signatures and then compared them with active messages on CAN for attack identification. However, these lagged in the identification of new and evolving attack vectors and incurred memory storage each time for new attack. More recently, machine learning models have been trained to flag discrepancies in CAN traffic and have been very successful. These techniques involve deep convolutional neural networks, support vector machines, generative adversarial networks, decision trees, convolutional LSTMs, and many more. All of these above approaches have been very successful, more than rule-based techniques in the classification of intrusions. However, there are some issues with the existing intrusion detection systems proposed. For example, software implementations of ML models directly on ECUs leads to sharing of critical compute resources within that ECU, and it also leads to isolation issues and high computational overheads, which interrupts the normal ECU functioning inside the vehicle. To mitigate this issue, ECUs are generally proposed as either standalone ECUs or on loosely coupled GPUs, accelerators. Now, standalone ECUs have integration complexity which they come up with, while GPUs, because of their high power consumption and factors like weight and size, are barriers. They are blocks which lead to barriers in their adoption, particularly in distributed intrusion detection system environments. We now talk about our proposed ECU IDS architecture. We choose a CNN model as our IDS, which goes through the training and validation flow for hyperparameter tuning and model optimization. From this design space exploration, we find a best performing lightweight model that is suitable as an IDS due to its accuracy metrics. This model then goes on through the WhiteSAI framework, with the first stage being the quantizer. The quantizer gives us an 8-bit quantized model and quantizes the weights, biases, and activations of the full precision floating point model. This quantized model can be further fine-tuned if there is any performance degradation. The fine-tuned model, they can then go through the compiler of the YTSI framework, which gives us an X model file for the model with instructions for how the DPU execution on the Ultra 96 V2 SoC will take place. The Ultra 96 V2 is preloaded with the DPU bitstream in the SD card, and it is also preloaded with the YTSI runtime libraries, which allow us to interact with the hardware accelerator. Our proposed architecture gives us very low latency per message to cater to critical communication demands in controller area network. It also gives us low power consumption, and it gives us a software controlled hardware IDS with the ECU functionality tightly packed with the IDS functionality in the hardware accelerator of the FPGA PL. So to tackle those deployment issues, we present a tightly coupled IDS accelerator on the Zynq Ultrascale Plus device. We use a quantized deep CNN based IDS that is executed on Xilinx deep learning processing unit. The DPU IP attaches itself as a slave peripheral to the ECU and allows it to be driven and controlled through the software APIs from the ECU application. We propose a 5-layer convolutional CNN as our IDS, which is 8-bit quantized. We now talk about results. We first look at our inference accuracy metrics for pre and post quantization of our model on the two attacks. We find that the performance after quantization does not degrade and hence can be used as an IDS. We compare the accuracy metrics of our IDS with those presented in the research literature and find that the performance of our IDS on attack identification for DOS and fuzzing attacks is either equal to or better than those proposed in the research literature. We also present the confusion matrix of our intrusion detection system in the research paper. We also compare the per message processing latency against the state-of-the-art IDSs and find that we see a 1.3x improvement in the per message latency as compared to the most closest MTH IDS intrusion detection system proposed in the research literature. We also quantify the resource utilization of our IDS and find that the IDS leaves enough resources for the other applications to be accelerated on the PL of the FPGA from the ECU. So in conclusion, we presented a hybrid FPGA-based ECU architecture that uses a machine learning model to detect onset of intrusions in CAN network. To achieve this purpose, we used the Xilinx YTSI flow to quantize, optimize, and compile our lightweight CNN model for execution on an off-the-shelf DPU accelerator. We achieve an average accuracy of 99.81% across both the attacks, which is identical to the state-of-the-art implementations. We find a 25% decrease in latency as compared to the state-of-the-art implementations with only 2 watt power consumption, which is 0.86 millijoules per inference. We believe that the proposed architecture can enable further research towards line rate distributed intrusion detection for CAN and automotive Ethernet. Thank you.